Salmon lice is a small parasite that is found in marine environment. It is a challenge for the aquaculture industry as it damages the salmon in terms of wounds and infections. A wide range of methods and devices has been developed through the time to reduce the risk of infections. Lice skirts are one of them. The lice thrive in the upper part of the water column. The basic concept behind the lice skirt is to create a barrier between the salmon and the parasite. If the parasite does not find a host, it will eventually die. The thought is that the lice skirts are permanently installed at the cages as a preventive measure. Consider a conventional circular aquaculture cage with a net. The lice skirt is installed on the outside of the fish barrier and is attached to the floating collar. The skirt is commonly made by dense, water-resistant fabrics such as tarpaulins and PVC. In this tutorial you will be presented to selected load parameters when modeling a lice skirt. Comparison of cages with and without lice skirt. Some troubleshooting aspects and suggested solutions are also included. Let us consider this from a hydrodynamical perspective. Conventional barriers such as nets have openings allowing water to flow through more or less unhindered. Introducing a lice skirt, the water particles are hindered from flowing through, and must pass on the sides of the barrier. Waves that interact will be accompanied by diffraction and deformation of the lice skirt. These effects will cause an increased pressure on the upstream side and the lice skirt will be deformed. This is commonly known as hydroelasticity, a time-dependent effect, where structures deform under the influence of fluids. The pressure increase will be transferred to the cage, and in turn lead to increased loads in the anchoring system. This is something to be aware of when planning an anchoring system at a fish farm facility. To model lice skirts in AquaSim, one can apply membrane and the load formulation lice skirt. AquaSim assumes that lice skirts always are modeled as a cylinder. Which part of the cylinder that is upstream and downstream of waves and current are kept track of. In this way, AquaSim is able to distribute the pressure field around the lice skirt in a realistic manner. To illustrate this pressure field, let us simplify the problem and consider fluid flow around a cylinder. If we change the view and look at the cylinder from above, upstream it will experience pressure drag force, and downstream suction drag. On the sides, the cylinder will experience lift forces. A consequence of AquaSim being able to keep track of what is upstream and downstream, is that each lice skirt must be modeled as its own component group. If you for example have a model of an aquaculture facility with 2x2 cages, you will need to model the lice skirts in 4 individual component groups. Moving on to AquaEdit, where we consider one conventional cage in the aquaculture industry. The cage consists of PE floating collar, net and anchoring. The yellow part here is the lice skirt. We are going to go through some of the load parameters that is important for lice skirts when conducting numerical analyses. Double-click the component lice skirt. Navigate to the section Load Properties. This tab provides input parameters that are relevant for impermeable fabrics. The drag coefficient, CD, is a unitless quantity that decides the magnitude of the pressure drag resistance. Let us again consider the simplified case with the cylinder. The pressure drag resistance is a force that is exerted on the cylinder when it is exposed to a fluid flow. Upstream one will have pressure drag and downstream suction drag. On each cylinder panel, the flow is decomposed into a normal and tangential component. Then the appropriate drag and lift force is found from this. The drag acts normal to the cylinder panel. Normally, this coefficient is determined empirically through experiments such as tank tests. The next parameter is the lift coefficient, CL. This is also a unitless quantity, and it decides the lift force on the lice skirt. The lift force regulates how much outwards force is exerted on the cylinder. The direction of the lift acts normal to the cylinder panel. The larger the lift force, the more oval the lice skirt becomes. Added mass coefficient/height. This parameter can be interpreted as a coefficient, or a height in terms of meter. For lice skirt, this should be interpreted as a coefficient. Let us call the added mass coefficient C. A mass. This coefficient is related to the 2D volume of the cylinder. And AquaSim is able to detect the radius of the lice skirt you are modeling. Added mass is the amount of water the cylinder must displace on the outside in order to move. Such mass is often interpreted as an inertia added to the cylinder. How this parameter should be interpreted depends on what you select as the type of diffraction load further down in the menu. In our case, flexible tarp is selected, and then the added mass coefficient is multiplied with the radius of the cylinder. For other methods, the added mass is found in other ways. Both added mass and hydrodynamic damping is interpreted as inertia that is added to the cylinder. Hydrodynamic damping dampens accelerations of the membrane panels in the cylinder. Applying flexible tarp as the diffraction model, damping is calculated in the same manner as the added mass. That is, the damping coefficient is multiplied with the radius of the cylinder. This was a short presentation of selected load parameters. The next step is to conduct an analysis of this cage with the present settings. From the export menu, one load condition is prepared. A wave amplitude of 1.4 meters, with a period of 4 seconds. In addition, current along x-axis is applied. Export the model and start the analysis. This analysis will take 3 to 5 minutes to complete, depending on your computer capabilities. Once the analysis has completed, the AVZ file can be loaded in AquaView. Impermeable nets are viewed as a membrane but with a darker rendering. When you apply lice skirt in your model, some additional results are available in AquaView. They are found under Results and Impermeable Net. Here you can view different results that is relevant for lice skirts, such as added mass, damping, internal pressure on the cylinder panels, pressure due to waves, and so on. Some of these options are useful for self-validation of input parameters. Plot the relative pressure to see how the pressure distributes around the cylinder as the waves passes. Change the view of the model to top view and start the playback. You see that the color scaling changes around the net. Moving to the next step, we are now going to compare this analysis with a model without any lice skirt. An analysis of the same cage is run, only with no impermeable barrier. The window to the left is with the lice skirt, and to the right is the one without. The response and deformation of the cages should be compared. To do so, plot the displacement in x direction for both files. You can see that the model with the lice skirt has slightly more deformed shape upstream, compared with the model without. This is due to the fluid particles are not able to flow through the impermeable barrier, and induces larger pressure drag upstream. At the same time, a larger suction drag is induced downstream, leading the floating collar to be pushed towards the center. You may also notice that the response of the floating collar is somewhat slower and more rigid. This is due to the trapped water inside the lice skirt, but also the water on the outside, that has to be accelerated in order for the floating collar to displace. Let us compare the von Mises stress in the floating collars. One can clearly see that the introduction of lice skirt has increased the load on this construction part. The von Mises level is higher, compared to the one without. As with all types of numerical models and analyses, one may encounter some challenges in terms of convergence issues. The cause of the convergence issues may be countless. It may span from improper discretization, human errors such as incorrect material data, lack of damping in your model, or too much damping in your model, and so on. There is unfortunately no quick fix, or one fix for all problems that you may encounter when working with dynamic analysis. But here are some tips if you encounter challenges with the convergence in your analysis model. Have in mind that you should, as far as possible, simplify the problem to narrow down possible sources of errors. Implement one change at a time in your model, so that you keep track of the effect of the introduced changes. Building FEM models, one will always encounter the trade-off between the level of details, number of elements, and access to computer power. The more comprehensive the model, the more time and effort is needed to solve the differential equations. In some situations, too few elements representing the lice skirt may cause the model to be too stiff, especially in the water line where waves contribute to large response. The user may then introduce additional elements on the lice skirt in the vicinity of the water line, as illustrated by this model. Here you see that compared with the model we analyzed, more elements have been added to the top. Have in mind, the convergence issue might as well be due to too many elements in the lice skirt. Making it too soft may introduce unrealistic large response. Try to either increase, or decrease, the number of elements in the vicinity of the water line. Let us consider discretization of time domain analysis. The discretization of the time domain analysis in AquaSim is governed by the two options, num total steps for waves and num steps for one wave. For hydrodynamic problems that encounter large deformations over short period of time, it can help to increase the number of steps. This better enables AquaSim to capture differences in forces and displacements between iterations. However, this will only have an effect to a limited extent. You will come to a point where increasing the number of steps does not have any effect. You will also have the trade-off that increased number of steps will affect the computational time of your analysis. The convergence criteria, and change dynamic convergence criteria, is simply explain the tolerance that regulates when AquaSim should be satisfied with one analysis step and move to the next. The larger this value, the larger difference in forces and displacements are allowed between each iteration in one analysis step. Having this too strict or too spacious, this can make it difficult to achieve convergence in the analyses. The user may try to tighten the convergence criteria, or vice versa, to see if this improves convergence. In this video you have been presented to selected parameters important for load appliance on lice skirts. We have compared results with and without this impermeable skirt, and at last some suggestions for solving numerical problems in your model. The full version of this tutorial, with all load parameters presented and more interesting information, is found online at aquasim.no.